So today we are so excited to have our colleague Dave Higdon join us. We were colleagues before when our group was at Virginia Tech. We have kept that bond for a long time. And if you want to learn a lot about Dave, you should watch the Researcher Spotlight interview that is on YouTube. You can learn about some cool experiments he did in the deserts of Nevada. But he is with the statistics department at Virginia Tech. He served as the department head for a while, and now he is on sabbatical, and we are thrilled to have him take time away from the sabbatical to share his knowledge and wisdom with us. So,
All right.
Dave, over to you.
Aaron, and thanks for the intro. And I forget, I have all these secrets out there on YouTube. Luckily, it's hidden in the masses there, so I don't have to feel too worried about that. But background-wise, like Aaron mentioned, I worked at Los Alamos a long time, so I did lots of work with putting big physics-based computational models together with experiments, and then trying to make inferences like what'll happen if we swap out materials or if something falls off, will reliability keep up? So the art of putting together a computational model output and observations is a lot of what I've worked on. And since working with the biocomplexity team, we've been taking some of these ideas to agent-based models and models that have stochastic output. So that is what I'm going to talk about today. I thought I'd make this pretty conceptual. So I'm hoping I'll try not to be too much with formulas, just sort of big ideas here about how this works. So people feel free to chime in. I'll get my chat window open. And if you got questions, let me know, and I can definitely indulge on that. So what I was going to do today is start with a pretty simple example, so you can just see sort of the main ideas behind the statistical thinking. And then, of course, it's me doing the thinking, right? So they're not going to be that complex of ideas. So we'll try it with a real simple capture-recapture model, counting how many fish are there. And then we'll get a little more complicated by doing this with a bigger agent-based model for an epidemic. Let me show you an agent-based model running here. So what this is we adapted this model that had birds flying around, and we made it fish, since fish are sort of the canonical example for this capture-recapture experiment that comes in statistics. That's answered very statistically, pen and paper style. But we thought, oh, here's a nice example that maybe we could highlight some of the ideas about how agent-based models kind of work here. And so all these little individuals here are fish. And what they do is they start out at some random point. And then what happens is if another fish is nearby and they're swimming in about the same direction, they'll kind of coalesce and start swimming in the same direction. So this picture started out very random looking, but now what's happening is the fish are starting to swim together in these schools. So they're just sort of schooling here. And what that's going to do is going to change the dynamics of this problem some. And so fish kind of swim together, they swim along, and they swim in schools. And then also what's going to happen is we're going to mark 100 of these fish and then let them swim around again and mix up. And then what we're going to do is mark another 100 fish. And we can tell by the ones that are marked together how many fish there are. So here are the fish starting out. They're moving around, and what we've got here is this net or this capturing mechanism. So it's a little contrived. You can also tell it's contrived because the way the fish don't look all that much like fish, but if you look really close, maybe they do. So what's going to happen is this thing is going to turn on and eventually start painting fish blue or marking them. So the fish are starting to swim in schools, and now we're marking these fish. And what happens is we mark them until we get 100 fish. So it's going to keep marking them until the count is 100 fish. So eventually in this population of fish, 100 of them are going to be marked blue. Still marking them there. And now it stops. So there's 100 blue fish in this total population. Also for the simulation, we know exactly how many fish are in this simulation. And I think it's somewhere around 1,500 fish in this particular simulation. Then they're going to swim around again and mix up. But these poor fish, they haven't learned statistics well enough. And so in our statistical models, what they do is they mix completely. So they're just uniformly at random all over the place. But these fish school and do things. And so they don't mix like they would statistically. And you can see that you've got these big patches of blue in some places. You got big patches of no marked fish in other places. And that wouldn't happen if you did put in the dynamics that this agent-based model has. So, okay, we let this roll a while longer. Now what's going to happen is eventually we're going to mark another 100 fish, and we're going to mark them red, except the ones that were already blue, they're going to be marked purple. And so we're going to keep going until we mark another 100 fish. And sometimes they're repeats, the purple fish, and sometimes they're new markings. So let me just go here towards the end here. So if you look at this thing, you can see we've got some purple fish. Those are the ones that have been captured twice. Or these are essentially what we call the marked fish out of the sample. And then we got some red ones and some blue ones. So what we did in this case, we went until we marked 100 fish. They're all blue. And then we let them mix up again, but not exactly mix up statistically, right? Mix up according to this agent-based models and the dynamics in that. And then after that, we're going to mark another 100 fish. And the ones that are marked both times give us some idea about how big the population is. And so that's the idea here, is that this is something that we do in statistical models kind of, almost trivially, right? If you ever take the class, like they go through this example so fast, it's hard to know what the heck is going on. But with an agent-based model, you have another way of attacking this problem. And so that's what I wanted to go over. So this is sort of our canonical example we'll look at to look at some of these ideas here. And I will get us into slideshow here. And of course, I've had lots of help on this project, so I'll talk about it and things like that. But as we talk to the agent-based models, I'm on play here.
May I just ask a quick question?
Yes.
So the marking did not seem random, right? When you were marking, it was kind of following a trajectory. It was continuously following some trajectory, at least from what I was gathering. So the marking is not a random process, right?
Yeah, that's right. And in fact, that's what we're relying on the agent-based model to do. It's not this, I would say it's random, but it's not this, uniform at random sort of thing, right? It's happening because the fish are moving and because you put down the net and mark them. And yes, that is the big point here, is that we think the way the fish get marked has a lot of structure in it. And that's something we might want to capture with an agent-based model. So yes, great question there. And that's exactly the point here, is that we're substituting what might be a statistical model out for this agent-based model that has randomness in it, but it has lots of structure in it. And of course, do we, are we correct in how we make fish, start following each other and things like that? Yeah, that's debatable, right? So the little behaviors inside these rule-based models is going to be a trickier part, but certainly that's more realistic than saying, once the fish hits the water, it just goes uniformly to some place in this whole ocean. So yeah, that's right.
Thank you.
All right, thanks for that. So we'll do fish, and then we'll get to an epidemic. All right, so I talked about the fish here. And so, like I said, basic idea, we mark 100 fish, we let them swim around, but not completely statistically uniformly random, right, according to this process, and mark another 100. And what we look at is a number of purple fish, the ones that were marked twice in the process. That's going to tell us something about what's the total population size. And then, like I was talking about, in the statistical model, right, there's no agent-based model going on. We just assume that when we do the second marking, it's from a simple random sample of that population. And if you do that, you can describe probabilistically exactly what is the sampling distribution of the number of purple fish, which I'm calling R2 here. So statistically, it's really easy if you make these assumptions, just not quite as realistic, right? All right, so that one simulation I did, I said it was around 1,500 fish started. So I picked out the N. And then what I did is I ran that agent-based model. And then what happened was we counted how many fish were R2, how many purple fish were there. And I think it's somewhere around 12 for that particular example. So maybe this little dot here corresponds to that model run. If I just said, what was the initial number of fish and how many were purple at the end? And so one dot is one of these big simulation runs. It takes a few minutes, like even for this little fish model. And then if we talked about this a little more formally, we'd say, oh, what we did is we generated an initial number of fish and put them out uniformly in this space. So that's the random part. How many fish was it? And then what we did is we ran this agent-based model and collected the number of purple fish at the end, R2. So I did it one time. It's just one of these circles in here, probably right around here. But now if we do it 10,000 times, here are a bunch of circles, which are basically the results of these computational model runs. And the fact that we're agent-based models is not super crucial here, but one of the properties that you can definitely see is if I reran this model at exactly the same number, 1,500 fish, the output I get for the number of purple fish is random for sure. It could be as high as maybe 20 and as low as even 0, I think. So the output is random. And it also depends on the number of fish you start with. If I start with a lot of fish way out here, then I'm not going to see a lot of purple fish, is what I've learned already just by looking at this plot. But if I start with much smaller numbers of fish, then I might see a lot more purple fish, up to maybe 70% of the sample might be purple. So there's what we get. And then, so I worked with Bionica, who's at MITRE now, and she does a lot of agent-based modeling. And so then I was asking her, well, all right, we did the fish, that's great. All right, these zeros here, my statistical sensibilities are kind of challenged here. What the heck happened there? And she told me that, what goes on is, like, if you run these things at kind of low population numbers, then what happens sometimes is, like, I just time it out that if you don't catch any other fish or you don't mark your whole 100 fish, I just stop the simulation and report zeros. And so what's going on is sort of a failed experiment here at the end. So statistically, I think, oh no, we should just keep going forever. They should be out there in that ocean forever until they get their 100 fish marked. But this is actually pretty realistic, right? If you really did this experiment and there wasn't a lot of fish there, like, there's no way you're getting to 100. And so this is also telling us about what are the number of failed experiments we got. And so it's informative here, right? If we get a failed experiment, it means the population size is probably pretty low. So of course you could kind of reason that out, but this is easily captured in an agent-based model that, part of the experiment process is actually being captured here. So I thought, oh yeah, that's a fun point here. All right, so here's the spread of what we see. And we can kind of think at different values of n, we get different spreads of the number of purple fish. And so if n is small, we'll probably see a lot more purple fish than when n is large. And this is what gives us some information that, once we actually do the experiment and record the number of purple fish, we'll have a better idea of what n is. And just as an example, here would be the analog of this plot if you did it through the statistical approach. This plot never showed up when I took these animal science population classes. But basically what's going on is you draw n from the same distribution we drew it from before. So we start with a number for the population size. And then we could just sample what is the number of purple fish if we just sample a simple random sample with 100 marked fish in the population. And so if we do it in this case, here's what we get. And you can see that our uncertainty is a lot tighter here, that even for 1,500 fish, like, there's not a wide range of what you can expect the number of purple fish to be. And so one of the advantages of this agent-based model over a very statistical approach is that even though you don't need to run a computational model to do this part, it's not going to be as realistic in its uncertainties. It's probably a lot tighter than it should be here. So that's what's going on here. So we can tell what the differences are between these two approaches. And now I'll go back to this results of the agent-based model. And I just all I did was make the plotting points smaller here. And so now we can say, here's our algorithm. We generate n according to this geometric distribution, but it really could have been anything. So this is essentially our prior distribution for the population size. And then we run the agent-based model with that population size and compute the number of purple fish. And now we could say, like, suppose we actually went out and did the experiment and we saw 25 purple fish. So we can say, all right, our observation is 25. Now what we can do is say, all we have to do is just keep the samples or the model runs for which that was the observation. And so in all of those cases, here are the plausible sample sizes that we've got here. So we can see that, all right, it might be a little bit over 1,000 if we trust this dot out here, but it's not going to be, 1,500 or more. It seems like that's just impossible here. So these cyan dots are really telling us our posterior distribution or uncertainty about what the population size is here. So if what we observe is 25 purple fish, these dots are saying here are plausible counts for the actual population size. And then formally, this is actually the posterior distribution for the population size. So this is both at the same time kind of just basic computational Bayesian inference, but it's also an example of approximate Bayesian computation. And so this is exactly the algorithm. You run a bunch of simulations from the prior, you simulate the data, and then just keep the observations for which the data simulated actually matches the data observed. And what you've got in these blue dots here is our draws on the posterior distribution. And you can compare that to what we get from the standard probability model. And they have a much tighter distribution for the population size than if you do this agent-based model. All right, so how do we present this to someone? Well, we could just take a histogram of these blue dots. And here might be a way to do that. So here's the standard statistical capture-recapture or mark-recapture model. And here's what we do when we do with the agent-based model rather than replace that statistical process of simple random sampling. And so, so this is a pretty good description of what do we think the population size is. What you notice here is we had to run this model 10,000 times just to get, what is this? I think less than 100 dots for which, or simulations for which we actually match the output. All right, so that's not a lot, right? So it's not hugely efficient. And then if you thought about any trickier problem, like, oh, this problem has a nice discreteness attached to it, so that if we have just integer numbers of fish that we might turn purple at the end of this thing, and so it's plausible we might match or have simulations get exactly 25. But if the output was something that's continuous, then even if it gets close, right, it doesn't match exactly. And so one thing is you have to figure out how close is a match if you want to do this approximate Bayesian computation. So that's a hard thing to do. And then the other thing is, yeah, it's very inefficient. So, a handful, 30-ish, 50-ish runs were actually telling us about the posterior distribution and the rest didn't. And so what we'd also like to do is be a lot more efficient. One way of doing this, and this is what we've done a lot in my life, because I can only learn a couple things in life, and this is one of them I learned, is to fit a response surface to the model output. And so this was talked about in the review, and I know a lot of people work on this project. So this is an emulator or a surrogate model for the simulator. So the computational model output, we might be able to model as a function of the parameters or the inputs. So here's the basic idea, is that here is this big cloud of 10,000 model runs. An alternative would be to run maybe 100 model runs at population size of 200, 300, 400, 500, all the way down till you thought it was enough out here. And then what we can do is look at the spread, and certainly the spread's a lot more when you have a small population size compared to when you have a large one out here. And so what we can do is fit a response surface to this output. So what's trickier here is that in my old physics world, the output was always just a single number. So if you put in exactly the same inputs, the output was the same. It didn't change here. But here, if I put in 200 for the population size, I get a lot of different outputs depending on the random seed I start with. So now what we want to emulate is both the dependence of the output on the model, and also you want to get the randomness modeled about right. And so what we do is called quantile regression or quantile cream here. So we'll fit a response surface to the quantiles together with the parameter input. Here it's just n. And so here I've just drawn a line at the 5th percentile for each of these collection of 100 points at these different values for n. And then the 15th percentile and so on all the way up to the 95th percentile. That's this top one. And so now what I want to do is fit a smooth response surface through these percentiles. Oh, and because I'm a statistician, right, I'll know like how uncertain I am when I estimate these quantiles. So I know I'm not going to go right exactly through these estimated quantiles. I know they're estimated with noise, but I also expect them to be smooth as the true population, or n, goes from something small to something big. So I think this black dotted line here of the 95th percentile should be something smooth going through here. And then also I'm going to expect monotonicity here, that lower percentile is going to be lower as I go down here. And so I can fit a response surface through these things with a Gaussian process, and no one will be punished with the details here. Oh, then I have to admit, my inner statistician, if I want to fit a response surface through counts, then I just feel like I really want to do a square root transformation. And the reason why is it makes this variance about constant all the way through. And this is an easier thing to do with statistical models rather than one here on this native scale where there's a lot of variance for small n and much less variance for larger n. So this kind of evens the playing field, but no big deal. Conceptually, nothing much to worry about except your response surface is going to have an easier time with something like this, that most stat models that we have or machine learning models do like this idea of variance being constant across things.
So in the plots you are showing till now, what is the independent variable? So is it n or there are other models?
Yeah, it's just n here. So that is the sample size. So that is the population size here. So that's an unknown. So it's a model parameter, essentially, right? It's the thing we want to infer about.
The y-axis is like, if you ran the simulation with everything else, all the other parameters fixed, how many, let's say, infections you're getting or fish you're seeing? Or
yeah. Right, that's right. And here it's purple fish, to be exact, for this exact example. But yes, it might be, in fact, in the next example, it'll be the cumulative number of infecteds.
Okay, thanks.
And the parameter here might be the transmissibility or something like that. So here, nice and easy, we just have one parameter and one output, but we might get more of those things as we kind of move on. Certainly, we'll get more model inputs or model parameters. So there's the response surface. And indeed, it is pretty smooth for the quantiles, right? Because it knew not to actually interpolate those quantiles. It knew they were estimated noisily with only 100 data points each. And so here's the response surface. And what you can see is you see this funny little bump here, which I thought like, oh, there's something wrong with the simulation. But this is that effect of those zeros, right, of the failures. And so you tend to get more failures out around here, and the response surface is actually accounting for that. So here's this feature that does have this non-linearity in it, or has this interaction effect that all these failures tend to happen, which give us a zero count. And so that's showing up in the response surface. And then also the big deal here, right, is the response surface is a function of the parameter and the quantile. So if you had just 200 for your response surface, the low possible end would be 0, but the highest possible thing you might see looks like it might be around, 50, 55 here. And I'm just showing you the posterior mean. This thing is also estimated with uncertainty. So you can imagine this surface kind of, oh yeah, there's plausible different surfaces here. They're all smooth, but it could be higher, it could be lower. So there's uncertainty attached to this surface. And that's also going to figure into the inference. So if you have a better response surface, you're going to get tighter inferences just because you don't have that uncertainty due to the fact that, oh, your response surface is uncertain. So here we definitely have some uncertainty attached to the response surface. Okay, so now we can put this together, and let's go back to our example where we had exactly 25 purple fish in the end. And now we're going to ask, well, what values of n are consistent with 25 purple fish? And if it was just the surface, right, it would just map out this little line going through there. But because it's uncertain, it's going to map out a region. So here's the plane at 25 purple fish here. And where does that cut this model? And it cuts this uncertain model. So this model is wiggling around. And so this is sort of the shadow of it. Where does it cut this thing? Oh, all these joint realizations of n and alpha that are kind of inside this blue are the ones that are plausible now, given that we observe 25 purple fish. And it's not aligned because we don't have certainty on what this output is exactly. Okay, and then we want to say, what's our inference about n? Well, if we just take all this area and push it down to the n axis and look at its marginal distribution, that's what we would see. And so that's what I'm showing here. So here's the marginal distribution for n using this response surface. And you can see that what it does is it looks a lot like what we got just from the sample that used approximate Bayesian computation. But it doesn't have this shot noise or this variation that comes with it. The fact that we have 30-ish points out of an infinity of them. So we're going to see some variation just from the fact that we're doing Monte Carlo estimation. So these are giving almost the same answer. The response surface does better in the fact that it knows to smooth these things out, that it knows what's shot noise and what isn't pretty much. It's also going to put in, it's not as certain, right? So it's not quite as exact as this inference, but it removes a lot of the shot noise. And so now as we infer about this unknown parameter, the population size, with the response surface, we can put it into this Bayesian machinery, and here's what we get.
How many runs of the ABM did you do for this?
All right. Yeah, good question. So this one we did 100 runs at population size of 200, 300, 400, up to, I think, you guys, your pictures are on the way, but up to here. So it's only 100 times, less than 20. Okay. So maybe.
So it's reasonable, but it's a small model. So this will come in later, I guess. Okay.
Yeah. So it's much smaller here. So here it's, 1/20th the size of the model runs that went into that giant ensemble.
Right.
And we get lots of information on the output.
Okay.
Yeah.
Good.
Yeah. So yes, and that's a big deal.
Yeah.
And hi, you did mention in a slide that the nugget would require some thought. Is there great sensitivity in the result depending on the nugget that you choose?
Yeah, exactly. And this one, I'll be very specific about this example to give you an example of it, and then it gets harder in other settings. But this one, we know that essentially we have draws from a distribution for each value of n here. And what we want to do is we want this response surface to go to the 95th percentile as we're going across here. And so because we can statistically estimate the uncertainty of the 95th percentile given a sample size of 100 and a little bit about what the tail behavior is of these distributions, we have lots of statistical tools to say, here's what I think the uncertainty is and where the true percentile is given our best estimate from each of these samples of size 100. So in that case, we know the uncertainty that we think the true percentile is, within a certain range here that we can just go back to sampling theory for percentiles to get to in this case. If you look at other computational models, it's not going to be so easy to do that. So for quantiles, it's easy. And in this case, we only had quantiles. But in other settings, you tend to have convergence error due to things like, how fine you make the grids and things like that are probably important for your inference, but you're not going to have easily at hand. And so those ones I think are harder to, you want to do something, and maybe you can let the Gaussian process model estimate those things for you by telling it, oh, we want the interpolator to be smooth, but how closely should you be matching the observations or the data that you do have that you're feeding it? Sometimes you can be pretty specific, like in this case, and other times you have to say, oh, we think it's less than 10%, so we can put some information in on that, but it's a harder thing to do. Did that make you happy at all?
Yeah, sure. Yeah.
All right, those are the main ideas behind what I wanted to talk about for this epidemic modeling here. And so what we have for an epidemic model here is, this is from the Ebola outbreak, I want to say 2013, 2014. So we've got network of connectivity and mobility for individuals within these 3 African nations that we're modeling here. And so the ingredients that go into this is populations, right? And populations are always made up of households, and households with kids and stuff move differently than households without kids. So trying to get this information is all really important. So coming up with what is our population, where do they live, and how do they move is a big deal. And of course, the general properties of a given location. Do most families live together in the same about area? Are they kind of scattered all over, kind of mixed in with the people that don't have kids? Where are work locations? So there's lots that goes into this. So I'm not going to talk about this much, except that it is a whole field unto itself, trying to figure out, well, how do you come up with a population and different data sources? What family sizes? Do you have census information? Do you have survey information? You definitely have geographical information that kind of goes into this. But in the end, different households will go to different places. Individuals in these different households will move around, and some will go to work, some might go shopping and then go home, and some might, take their kids to school, maybe go shopping and come home. And so we have this intricate connectivity that over time, right? So it's dynamic as to who is in the contact with whom for how long over the course of a given day. And so this goes into how the disease is going to propagate over time. And certainly as behaviors change, right, this mapping or this connectivity or this transmissibility or who's in close to whom is going to be changing as well. So here I just want to get to, but I'll give this short shrift. I'll go through this kind of fast just so you get the idea here that this model has 5 parameters in it. Probably the biggest one is this transmissibility one, and other ones about how you initialize this thing. And we had this also in the agent-based model, right? We put everyone out there, all the fish out there uniformly, but now we're a little more thoughtful here. How do we seed the simulations, hospital parameters, but also things like parameters that might govern behavior as well. And so now what we want to do is run a design set of simulations over this 5-dimensional parameter setting. And just here, like we did a design set of simulations over this 1-dimensional parameter setting here. So it's analogous to this. So here's the design we actually have. So it's 100 different input settings, and each input setting is determined by these 5 parameters. And so what we try to do is fill in the spaces. And so it's a space filling design, and this design tries to fill in 2-dimensional margins pretty well, but it's hard to fill in the 3 or 4-dimensional margins and not end up with designs that have weird properties. So we want to do space filling, and we definitely want to ensure we space fill at least in 2-dimensional margins well. And so this is just a visualization of this 100 by 5 design that we have for a Latin hypercube. So what we're going to do is run the agent-based model 100 times at each one of these 100 settings that you see here. And in addition to these projections here, I also have 3 design points kind of labeled here. So I have A, B, and C. And just when you look at the output, you'll say, all right, A is a specific set of 5 parameters here, even though it shows up in a lot of these plots, like one of these design rows corresponds to A, another one corresponds to B, and another one corresponds to C. And I just mark those because they have different looking behaviors when we look at the simulation output. And so next we've got the simulation output. And what you're seeing is the cumulative number of infecteds in the gray lines as a function of time for the simulation. And so, for instance, at this one input setting, there's 100 gray lines. Some of them go up. Some of them, the epidemic dies out pretty early. And then, of course, the cumulative line is just going to flatten out. There's no more new infections. So they have this kind of behavior where for some parameter settings, you might have a really big epidemic, or you might have none at all with the exact same parameter setting. So this uncertainty is going to be pretty important to capture. And this black line is just a cut at what the total number of infecteds were from information that we got. So it just gives you an idea of which ones seem to be consistent with the data. But certainly at this parameter setting, yeah, a lot of these runs at this parameter setting seem to be consistent, but some of them don't look consistent at all. So in some sense, this parameter setting is plausible, but it's going to be at the high end of what you might get from this parameter setting. So I've got parameter setting A here, which is largely a pretty tight bunch. So statistically, it's what we usually think, right? That there's kind of like a mean and kind of variation around it that's pretty tractable. So this is kind of a typical looking thing. C is a little bit trickier, right? This one bifurcates, but it kind of does half and half. In half the runs, the epidemic dies out pretty quickly. And then the other half, it continues growing over time. Of course, neither of these two sort of modes for this parameter setting are consistent with the observations. So this shouldn't be a parameter we're entertaining in the inference in the end. And then B is one I would say is hard, that most of them, the epidemic kind of continues along and keeps growing. But for a small percentage, the epidemic kind of just flattens out and ends. And so this is an uncertainty that's going to be hard to capture. And we're going to use this quantile approach to go after this. So now what we'd like to do is say, pick any new input setting. So you might just say, pick one of these sides and then guess what the simulation output is going to look like. Not just the mean of the simulation output, but also the spread of it. And of course, we want to do this for new parameter settings that we haven't even tried yet or run yet, because that's what we want to base our inference on. What parameter settings seem to be consistent with that? All right, so a few details which are not super important here, but how do we represent this cumulative number of infecteds? And in this case, what we did is we just did it with a basis approach. So we just said it was an overall mean, this is 5,0, plus a linear combination of bases. So I'm showing you 2 of them, but I think we go more, but it doesn't help that much. The 2 do most of the work here. And then what happens is a coefficient in front of these bases is what depends on the parameter settings. So basically, we're fitting a Gaussian process for the coefficients here for each of the different basis elements. And so the first one's going to get a lot of the variation. It's going to be fairly smooth looking, and then the later ones tend not to be as smooth. This seems to happen pretty typically in these cases. All right, so basis representation for the simulation output, because it's not just a single number, right? It's this whole line of cumulative counts. And then doing the quantiles is also a little bit tricky because it's a multivariate sort of thing. But we were able to do, turns out this data is fairly well behaved, that high values at the end of the time of the epidemic are aligned very well with high values at the beginning of the epidemic. So the trajectories don't cross each other very much, and this makes it easier. But here I'm showing you 5 quantiles for these epidemics, the low, the middle ones, and the high ones. So the blue is high, pink is low. And you can see that, the low quantile is in this low region for this one parameter setting B. And then also you can see same thing for C, that most of them do well, but some of them are this way. So now we're going to fit the response surface through these quantiles rather than through all the data. And this is just for practical reasons, but also it's going to help us with our inference down the road. We can see how well is our response surface doing. Of course, it does, anything would do well for this case, this parameter setting A. But so what we did is just hold out these different parameter settings. So the runs that correspond to these settings, we held them out and then tried to simulate the population of curves. And so we can see how well do we do at the 5th percentile, the 27.5th, the 50th, and so on. So now a good thing to look at is how well do we do on this low one? And then we track the other ones here. And yeah, it seems okay, but it's not great. And certainly we have a lot of uncertainty attached to this as well. And part of this is the fact that we're just estimating quantiles with only 100 model runs. So we're going to have some uncertainty attached to it. And part of it is the response surface. We use a Gaussian process here. It might not be the best thing to do. So I think there's room for improvement on how wide is this uncertainty, this gray band part. But it's doing pretty well on capturing the variation, that it knows that, oh, for low values of the quantile, it's pretty low, and then it quickly jumps up to higher values as you move up the quantile ladder here. And so it does reasonably well here, but definitely could be better. But now we can go ahead and put this, well, we can put this together. We can also just look at our emulator or our response surface model and ask questions about what parameters are most important. So this isn't a formal sensitivity analysis here. What I'm doing is I'm just varying the first parameter, transmissibility, holding the other parameters fixed at their central points, and just asking, all right, how does the simulated cumulus sum, how does that change as I move the parameter from low, this dark line, to high? And I can see that, oh, it's doing what's expected, right? As transmissibility goes up, the simulated epidemic count goes up. All right, so that all works well. So we can look at these other parameters and see what their effects are this way. So this isn't just a main effects plot. So it's not showing everything, but it gives you an idea, like, okay, are we capturing this thing well and all of that? Okay, and now we want to put this together and make the inferences. So there's a lot of machinery computation going into this, but basically the ingredients are that response surface over the quantiles and then Markov chain Monte Carlo sampling. And so here's a representation of the 5-dimensional, but now it's going to be 6-dimensional because we also have quantile in there, right? So here's the 6-dimensional point cloud for which we think the simulation will give us simulation inputs that seem to be consistent with the observations. And so this formally is a posterior distribution. So this is describing the uncertainty in these model parameters. And you can see that, oh, for instance, the quantile, like, oh yeah, what we got here seems to be at the higher end of the percentiles here. So if we trust the model anyway, some hints that, oh, what we saw was a bad case given this epidemic or given these model parameter settings. But transmissibility gets a fair bit of information. Same with the initialization parameter. It was pretty important that it seems to be at this lower end. And we can also see the trade-off here. So it sort of makes sense that we have some dependence between how many are seeded in the epidemic modeling and what quantile we pick. And so if we have a low number being seeded, then we probably are at the higher quantile. But if we move the quantile down a little bit, then we're probably at a higher number for the seeding. So you can see the trade-offs going on in here, and those kind of make sense. All right, so we got this 6-dimensional parameter uncertainty that we can run through the model or run through the emulator, and we can get the model predictions from that. So if we just run the parameter uncertainty through the emulator, here's 95th and 5th percentiles of the model predictions going on. The other thing we want to do is we want to acknowledge the fact that simulation, even at the right parameter sets, it's not necessarily going to be reality. And so we add a stochastic component that says, oh, reality may differ from the simulated count in some systematic way. And so here we fit a Gaussian process model to it, but the model framework is set so that if we can fit it with the model, then and you can make this discrepancy term 0, go ahead and do that. And so here at 20 weeks, it doesn't really see a need for this discrepancy term. And so it estimates it to be 0. And so now we can say, all right, our prediction for reality, given everything, corresponds to these bounds here. And then, of course, with the agent-based model, we can look at other features of these realizations or these posterior realizations of plausible predictions or plausible epidemics. So here, what you see in this cyan is a posterior sample of these plausible epidemics. So they weren't run by actual model runs, but they were run through the emulator. And now when we look at a given epidemic, so here's a really extreme one, we can pick off features that might be important, right? So here's the peak, here's the number infected at that peak, and here's the timing of that peak. So for instance, we can say, when do we think we've reached the peak? We can make inferences on things like that. And then just to see what happens. If we just have 13 weeks of data, here's our uncertainty, and it's pretty wide. But then if we get more and more data, 26 and 35 and beyond, we can look at how the inference changes. And one of the things that does happen is if we get more and more data, our uncertainty isn't changing that much, but then we eventually do see that the model and reality aren't really aligning completely over this whole 40-some week period. And so now it is fitting a term for this discrepancy, and it's saying it's generally moving the count down in the later time periods because the model is over predicting for these later time periods. All right. Here's just sort of more formal looks at the peak number of cases that you get and the total epidemic size. So we can look at things like that. And this also shows that in the initial part where we have just 13 weeks of information, we have a lot of uncertainty on this. And this is on the log scale. So this is a huge amount of uncertainty. And then it starts going down as we start getting more information. After week 26, we really don't see a big change. And this is pretty common when you bring big models into these inferences. What happens is the models have lots of structure in them. And that means eventually your amount of information you're going to get is going to lock those things down as much as it can. And extra data isn't going to help you that much. And that's what's going on here. Of course, with that discrepancy, you actually do learn something about the discrepancy when you have a lot of data, but it tends not to help you much with the predictions. It's just changing your prediction from exactly what the model is saying to the model plus a discrepancy piece. So it's going to do something different here. So I'm going to end it there and just say, usually I tell this to the stat audience, right? And so I like to reiterate that the agent-based models, right, they have pluses and minuses of them. But the really nice things is how they kind of map to reality, that if you want to close schools or do certain sorts of management mitigations, you can actually do them in the agent-based model and look at the output. And so it maps in this way to reality. That's really nice. It's also a very nice tool for running these what-if scenarios and things like that. Certainly computationally, they tend to take a long time to run, and they're a bit unwieldy to work with. So on the low end is lots of computational costs. And mapping them to reality, that the more you try to match with your ABM or any computational model, the more you're going to stress it. So it can often match one or two outputs with given parameters sitting pretty well, but doesn't match 10 different types of outputs. That's a harder thing. All right, we had to deal with the randomness, and so that was a hard thing. We did this quantile trick here. That worked okay for this case. Is it going to work in these other cases? I'm not sure. And certainly we saw some places where the model did match reality. But overall, I think it's a very nice way of putting structure into your problem that's different from our usual statistical or mathematical or probabilistic approaches. And certainly it doesn't have to be all one or the other. That, as you can see, there's hybrids, there's pieces of different things in a model or a formulation like this. So I think there's lots of room for us to keep figuring this sort of stuff out. And modeling epidemics is certainly a place to be working, that there's a lot to be done in that area. So I will leave it there. And thanks for the questions and listening. And more questions are always welcome. Thanks.
Thank you so much, Dave. Fantastic, as we knew it would be. All right. If there is anyone with a question, feel free to raise your hand, put it in the chat.
Oh, I definitely like the clapping hands. Thanks for that.
Clapping hands from Lakshmi. Yeah, or perhaps you just did such a great job. Oh, here we go. Here's a question. All right, Thomas. Go ahead.
Hi. Thanks very much for the talk, and apologies for the background. What I wanted to ask you is, I appreciate that I'm asking about a detail, but you did comment on when you chose the experimental design for learning the emulator, you did say that you favored a Latin hypercube design. And here, I want to pick your brain on this choice, because you made a comment that other static designs may not necessarily work well in lower dimensional projections. But there are static designs that are explicitly designed to do this, like maximum projection designs, right?
Mm-hmm. Right.
And the other thing is, in a general case, and yes, the computation. So that's question one, maybe. And then I'm going to ask you about a dynamic alternative. So why not, let's say, a maximum projection design, which would be my go-to thing for a 6-dimensional.
All right. Yeah. All right. So no, those are good things to do. So I didn't want to be very dogmatic that, in fact, just random designs end up working really well, just because you tend to have lots of structure in what you're going to be fitting here. So let me not be very dogmatic at all about designs, that lots of things seem to do well. And for the static, what are you going to do for your first try out there? I think that's, lots of people write papers about them, like all of them seem to do about as well. In fact, if we come up with sort of our best new design and compare it to just random points in this space, the random points wins, maybe 40% of the time.
True. That's fair. Yeah.
Yeah. So it's a lot of times it's features that you end up, and you're hinting towards this, right? It's features of the response surface that, oh, you want to be lucky in your design to align with those in ways that are going to be important for you getting a good response model. And that tends to be not a dimension agnostic thing going in that you might start with. You might learn that, oh, a few of these parameters are really important, and these two and those two have interactions that are important. Knowing that would probably change what you would do for that design.
So I take it I would not be committing any fatal sin if in a problem I would start in with a Latin hypercube.
Yeah. And in fact, starting with a random design is not a bad way to go, or whatever is kind of just laying around, because your first cut, like, oh, the modeling guy's like, oh, you want me to run this now? Like, oh, they just have something laying around. That's not a bad first thing to work with too.
And because in this case, the model is behaving relatively nicely, right? I mean, it's not a horrendous function on the parameters, and it's not crazy rough. It seems smoothish. Yeah. So wouldn't a dynamic design where you start with a static thing, you learn your emulator, then you say, let me pick the next design point to optimize some sort of a criterion, like McCain or whatever. My heuristic would be that those things would tend to work well in smoothish.
Yeah. All right. Yeah. So that is a great point, and certainly we work in this more dynamic sorts of designs or active learning kinds of approaches for these sorts of things. And yes, that is a good way to go. All right now, like, first, if you get a statistical blessing from me, it's like the most liberal, Catholic out there. Like, oh, it doesn't mean you're going to go to heaven anyway. So I will be loose on the blessings for sure. And then also just personally, like the experiences. First, on problems, usually a lot of the work is formulated in such a way that now it's easy and now almost anything will work. I feel like most problems that look hard, but you can do, you just found a way to make them easy. And so in finding the way to make them easy is a lot of the art here. And then in the end, you're like, oh yeah, any design would have worked here. But it's trying to formulate in such a way that you get to that point, and I think is sort of the harder thing. But yes, now if you really think like, oh, what I need to do is get this response surface to match better, and I've got features here in these certain places that are going to be important for the inference, then yes, then these adaptive designs are going to do better with those sorts of things and how you can learn. And then also that's going to couple with your model that the Gaussian process is still kind of a little bit agnostic in dimensions and things like that. And so it's hard for it to tell you that it has features here you need to start throwing more points at. And then you might want a model that can find these features to tell you that, oh, I have more uncertainty in this one place, in a way that maybe Gaussian processes, because they only care about just where your points are, not what happened at them, will do. So yes, I think those are good ideas. But I'll tell you
very much.
And where I've screwed up in life, though, is when I've been too smart on my designs. That I did some design and then I turned out in some weird dimension, things were on some manifold, and we didn't learn about something that ended up really being important. And it was an artifact of me trying to optimize something that had some other side effect that made it a really bad design in some way I didn't figure out until after the fact. So this is why I like these just random designs too, just because, all right, they may not be optimal, but I probably didn't screw them up by trying to be optimal.
Thanks very much for this, and I really appreciate it. Thanks much.
Awesome. Thanks for the question.
Thanks, Dave. Really interesting talk. So one question about like the smoothness. So in many epidemic models, you have these phase transitions, right? So with transmissibility, if you're varying, you go from like below, so there's a threshold, right? You go from a small infection to large infection kind of regime. So will the emulator be able to replicate those kinds of things? Or?
Yeah. All right. So I'll give you a couple variants of answers on that. one of them is sometimes that shows up in the randomness, that if you're at a transmissibility that's near this border, then if you get a high initialization, it might end up kind of exploding for a while, that epidemic, or it might not. So we saw that in just the randomness of these things, that we saw, oh yeah, sometimes like you don't even have to change that parameter and it has this phase change almost. All right, so one part is, oh yeah, that's in there, and then does quantiles capture that? Yeah, sort of, but I think you can do better, is my guess. Also, like you were saying, the response is not going to be smooth. You are going to get a big change for a small change in a parameter. There is that's the enemy of usual kind of response surface modeling, and ways to overcome that enemy are more sampling around there. So this is where that adaptive sampling would be important. If you could figure out, oh, do things change real suddenly in a certain spot, you're going to want more samples there to figure out when that is. And then you're going to want a model that's not necessarily, using what it learned over here in terms of smoothness and things like that. So it means more data and, more thoughtful response surfaces. But I also think this is where kind of the advances of machine learning are going to be in a good spot to help us out. That a lot of these deeper neural networks, even deep Gaussian processes, things like that, are going to be able to do that. They're just going to need more data in general to do that. And that means more computational model runs or ways for us to figure that out.
So I guess adaptive sampling would be one way. So is there a framework for how to figure out where to sample? So I guess you have to first figure out where you have most uncertainty and then sample more there, right?
Yeah. And in fact, I will send you a paper. I'm not promoting it like we did it with a deep Gaussian process, but we want to go away from Gaussian processes because they're very stubborn about what you learn over here in variance. It's the same thing you learn over here. It's very stationary in some ways, and we want to go away from that. So I will send you a paper, but it has lots of references. But I think it's these deep learning sorts of approaches, because then you get very different. You end up warping spaces, and you get different things, behaviors in different places. Yes, and then you always have your adaptive learning or your adaptive design kind of tailored to the response surface model that you're using. That it's hard to make it kind of generic adaptive design.
Yeah, thanks.
All right, we are just about at time. Thank you again so much. Fantastic.
All right, you're welcome. Thanks, you guys, for listening to me and nodding your heads like you understood. Or I just imagine that anyway. That's what I like about doing it on Zoom. I just imagine everyone nodding and thinking, "Oh, what fun this stuff is!" So thanks, you guys, for listening.
Absolutely.